In everyday life, movement usually has an obvious cause. An engine drives a car forward, a current carries a boat downstream. But when whole galaxies move through space, what is pulling them is much harder to identify. Our galaxy is moving too, not just the Sun around the Milky Way, or the Milky Way among nearby galaxies. The entire local group is drifting through the wider cosmos at about 627 kilometers per second, roughly 390 miles per second. Astronomers can measure that motion against the cosmic microwave background, the oldest light we can observe. The measurement gives them a direction and a speed before they have a clean view of everything responsible. That's the awkward part. We can see the drift more clearly than we can see the gravitational landscape producing it. For years, that mismatch gathered around a wonderfully ominous name, the Great Attractor. It sounds like one enormous object hiding behind the Milky Way, quietly dragging galaxies toward itself. Perhaps a gigantic black hole, perhaps something worse. It isn't a cosmic vacuum cleaner, and it isn't coming to swallow us. Gravity works across immense distances, and the sky in that direction is difficult to map. Our own galaxy blocks the view with stars, gas and dust, so astronomers had to work patiently around the obstruction, using motion itself as a clue. That leaves us with a peculiar situation. The pull is measurable, the source is partly hidden, and the map needed to explain it is larger than the neat object its name encourages you to imagine. Tonight we'll begin with the motion we can trust, then follow the evidence into the obscured sky. The answer grows wider and stranger only after that first measurement is secure. If you enjoy exploring questions like this with me, subscribing helps others find them too. Liking and sharing the video helps even more. Now, let's begin. You would expect the oldest light in the universe to look evenly spread around us. It comes from every direction after all. It has crossed space for nearly the entire history of the cosmos, so an all-sky map of that light ought to look almost perfectly balanced. And at first glance it does. The cosmic microwave background is a faint afterglow left by the early universe. Its temperature is remarkably uniform across the sky. But look closely, and the whole map has a slight lean. One broad side appears a little warmer, the opposite side appears a little cooler. The obvious thought is that the universe itself must be lopsided. Perhaps there is more hot material in one direction, or some enormous cold region on the other side. But the pattern fits a much more familiar experience, moving through something that surrounds you. Imagine standing in a still room and feeling a faint draft across your face. You know there is motion before you know which window is open. The warm and cool sides of the microwave sky work in a similar way. They tell us that our local galaxy system, the local group, is moving relative to this ancient background of light. As we move toward one part of the sky, the light arriving from that direction is squeezed slightly. Its measured temperature rises by a tiny amount. Behind us, the light is stretched slightly, so it looks a little cooler. This is a Doppler-like effect, though the old light is not chasing us through space. Our motion changes how we measure the light in front of us and behind us. That broad, warm to cool pattern is called the cosmic microwave background dipole. It gives astronomers a reference frame that reaches far beyond nearby stars and galaxies. Against that frame, the local group is moving at about 627 kilometers per second, about 390 miles per second. That is roughly 627 kilometers every second. Our galaxy, Andromeda, and the smaller galaxies traveling with them are all riding inside that motion. You cannot feel it. There is no wind against Earth and no vibration under your feet. The clue is written across the entire sky as a difference so small that careful instruments had to pull it from the afterglow. When astronomers compare this motion with maps of nearby galaxies, such as the 2-mass redshift survey studied by Pirina Dogdu and her colleagues, they can ask whether the visible distribution of matter points in the same general direction. Much of it does. Gravity has been tugging on the local group for a very long time. But the dipole does not identify one object and close the case. Work by Martin Schmolt and others showed why the accounting is harder than that. Surveys cover limited distances, some regions hide behind the Milky Way, and several concentrations of matter may contribute to the pull. The microwave background establishes the motion. It does not hand us the name of a single culprit. So we begin with the observation before any famous attractor or dramatic label. The oldest light has a warm side and a cool side. Our local galaxy system is moving through its frame at about 627 kilometers per second, and the sky itself quietly records the drift. But if cosmic expansion is already carrying distant galaxies apart, what kind of motion is this? Once you hear a number that large, it becomes hard to keep thinking in slogans. But speed is never just a number. It always means motion compared with something else. Your coffee may be sitting still beside you while both of you cross the countryside at 60 miles an hour. Inside the train, the cup isn't moving. From the platform, it certainly is. We need the same kind of care here, because Earth is carrying us through several motions at once. Right now, you're moving around the Sun. The Sun is circling inside the Milky Way. The Milky Way and its neighboring galaxies are also moving together through a much larger cosmic landscape. Those motions have different speeds, different directions, and different reference frames. Bundling them into one claim that we're racing through space doesn't tell us very much. So strip them away one by one. Set aside Earth's orbit around the Sun. Set aside the Sun's path through the galaxy. Set aside the ordinary rotation of the Milky Way. The motion picked out by the dipole is something broader, the drift of our local galaxy neighborhood compared with the CMB frame. That neighborhood is called the local group. It includes the Milky Way, Andromeda, the Triangulum galaxy, and dozens of smaller galaxies held together by gravity. Public titles often shorten the result to the speed of the Milky Way. That's understandable. We live here, and our galaxy fits neatly on a page. But the measured unit is broader than the Milky Way alone. Relative to the CMB frame, the local group is moving at about 627 kilometers per second. That's about 390 miles per second. About 390 miles every second in a particular direction. The direction changes the answer. This isn't the general fact that planets orbit stars or that stars circle galactic centers. It's a directional drift left over after the familiar local motions have been accounted for. Imagine several arrows laid over the same patch of sky. One marks Earth moving around the Sun. Another marks the Sun moving through the Milky Way. Another marks galactic rotation. Remove those, and one long arrow remains for the local group's motion relative to the cosmic background. That gives us a clean measurement, and there's some relief in finally naming the right motion. We're not talking about every movement happening at once. We're talking about one chosen comparison, like stepping off the train and measuring your walk against the platform instead of the carriage. But a speed and a direction still don't reveal the cause. The figure is approximate, and it doesn't provide a final breakdown of every gravitational contribution along the way. It tells us that our local group has an extra motion beyond the smooth recession expected from cosmic expansion. Something has shaped that drift across the surrounding universe. So what distribution of matter could pull an entire neighborhood of galaxies into that one long arrow? The natural impulse is to follow that arrow immediately and put something at its tip. A huge cluster, perhaps, some hidden concentration of galaxies with enough gravity to tug our neighborhood across space. We like causes more than clues. Once an arrow has a direction, the mind wants a culprit waiting neatly at the other end. Astronomy doesn't always arrive in that order. Imagine entering a dark room and finding footprints across the floor. You can measure their spacing. You can see which way they turn. You might even tell that several people moved together. But until more of the room is lit, you can't reconstruct everything that made them choose that path. The motion came first like that, not as a photograph of one enormous hidden object, but as a discrepancy between the flow astronomers expected and the flow they measured. The map gained an arrow while parts of the territory behind that arrow were still blank. And the arrow wasn't really about the Milky Way by itself. Flow studies compare the movement of our local group with nearby groups and larger patterns around them. In 1999, a team led by Richard Schmolt examined that wider flow. asking how much of our motion could be accounted for by the galaxies mapped across the surrounding universe. The scale changes what the map can show. A single galaxy can have its own local complications. Several groups drifting in a related direction point toward a much broader distribution of matter. That comparison is slow work. It asks whether the same broad pattern appears across different groups and distances, and whether the motion holds together when the map is redrawn. The patience is part of the evidence. That's why the word pulling needs a little care. Gravity contributes to what astronomers call peculiar velocity, motion measured against the smooth expansion used as the background. It doesn't mean every turn of the Sun, every orbit inside the Milky Way, or every jostle within the local group has one distant cause. In 2023, Brent Tully and his colleagues again treated these flows as motions defined within a chosen frame. Change the comparison, and the number you describe can change with it. The measured drift is solid. The full accounting of the mass behind it is harder. Some of that difficulty comes from an awkward fact about our view. Part of the relevant sky lies behind the crowded plane of our own galaxy, where dust and stars make distant galaxies harder to trace. The missing detail wasn't a license to invent a monster in the dark. It was a reason to combine motion surveys, galaxy maps, and later observations until the room became clearer. So astronomers weren't clueless. They knew the direction of the footprints. They had estimates of the shared motion. They could test whether mapped matter explained enough of it. What they didn't yet have was one complete, evenly lit reconstruction of every mass contributing to the flow. Only later did a memorable name begin to dominate the story. The clue was older than the label and less neat than the view the label suggests. That order is useful. It keeps us from turning an observed motion into a single object too quickly. First measure the departure from the expected flow, then ask how matter across a wide region could produce it. And before we follow the arrow any farther, what exactly makes a velocity peculiar? Most people learn one large cosmology sentence first. The universe is expanding, so galaxies are moving apart. That can make any talk of galaxies being pulled somewhere sound like a contradiction. If space is carrying distant galaxies away from one another, how can our part of the universe also drift in one particular direction? The answer is that both motions can happen together. One is the broad, smooth pattern. The other is a departure from that pattern. Imagine a river carrying a line of small boats downstream. Most follow the main current, but one passes near a slow swirl beside the bank. That boat keeps moving downstream with all the others. At the same time, it slides a little sideways, away from the path you would have predicted. The downstream motion is the background flow. The sideways drift is an extra motion layered on top. Cosmologists call that extra motion a peculiar velocity. The phrase sounds as though a galaxy has started behaving badly, which feels slightly unfair to the galaxy. Here, peculiar only means different from the velocity predicted by the smooth Hubble expansion. You work out how a galaxy should move if it followed that average expansion perfectly. Then you compare that expected motion with the motion you observe. The difference between them is its peculiar velocity. Imagine standing on a moving walkway at an airport. Even if you stand still, the walkway carries you forward. If you begin walking diagonally toward the other side, your total motion now has two parts. The walkway still carries you. Your own steps add a deviation. A galaxy's measured motion can be separated in much the same way. The expected recession from expansion, plus an additional movement relative to that smooth pattern. The river and walkway comparisons help, but only up to a point. Space isn't a liquid or a conveyor belt. Galaxies aren't being pushed through cosmic water, and there's no drag force pulling them off course. The background pattern comes from expanding space. The added motion comes mainly from gravity acting across an uneven landscape of matter. Matter isn't spread perfectly evenly. Galaxies gather into groups, clusters, walls, and still larger concentrations. Between them lie regions with much less matter. Those differences matter because gravity responds to where mass is. A galaxy can move away from us as the universe expands, while also falling slightly toward a concentration nearby. Across larger distances, whole groups and clusters can share an added drift. They move with the average expansion while being tugged away from the average path. So expansion and local gravity aren't rival explanations. They occupy the same measurement. One gives us the background expectation, the other explains why the observed motion departs from it. In 2006, Pirin Erdog-Du and colleagues used large galaxy surveys to compare peculiar motions with the uneven distribution of matter around us. That comparison gives the extra velocity physical meaning. It isn't merely an odd number left over after a calculation. It carries information about how mass is arranged, including matter we can't see directly but can trace through its gravitational effects. And this is what pulling has meant all along. It's convenient shorthand for a non-Hubble part of our motion, superimposed on the universe's expansion. Nothing here asks us to abandon cosmic expansion. We're separating the broad flow from the directional drift hidden inside the total velocity. Once those layers are apart, we can finally ask the useful question: what arrangement of matter could produce the peculiar velocity we actually measure? It would be lovely if one clean spectrum could settle this. Point a telescope, spread a galaxy's light into its colors, read the redshift, and there's your answer. Except the redshift gives us the whole motion along our line of sight. It doesn't label which part came from cosmic expansion and which part came from the galaxy's extra drift. Imagine walking through an airport on a moving walkway. Someone watching from the terminal sees your total speed across the floor. But that number combines two things: the steady motion of the walkway and your own steps. You might be walking with it, against it, or standing still while the floor does all the work. To learn what your feet are doing, the observer needs the walkway's speed first. Then they subtract it. Astronomers face the same piece of arithmetic, only with galaxies. The observed redshift tells them how quickly a galaxy appears to be receding. They also need an independent estimate of its distance. At that distance, the general expansion predicts a certain recession speed. Subtract that expected motion from the motion inferred from redshift, and the remainder is the peculiar velocity. So a redshift by itself isn't enough. Without the distance, you know the total motion, but you don't know what should be removed. The spectrum provides one half of the comparison, the distance estimate provides the other. This makes distance catalogues unusually important. Astronomers gather thousands of galaxies, estimate how far away each one is, and compare those distances with their redshifts. In 2023, Brent Tully and his colleagues published Cosmic Flows 4, bringing together tens of thousands of galaxy distance measurements. Each galaxy became another dot on a large, uneven map. Imagine those dots arranged by distance. A smooth trend runs through them, showing how recession speed generally rises as distance increases. That trend represents the expected expansion. The offsets from it carry the motion clues. A galaxy sitting away from the trend may be receding a little faster or slower than expansion alone predicts. One offset tells you very little. It could reflect genuine motion, or simply an uncertain distance. But many offsets, scattered across the sky, can reveal a shared flow. If neighboring galaxies keep leaning away from the smooth trend in related ways, the pattern becomes harder to dismiss as measurement noise. And the distances are the awkward part. Galaxies don't arrive with neat labels showing how far their light has traveled. Their distances must be inferred from other measured properties. Individual estimates can be noisy, and different methods don't fit together perfectly. Change a distance estimate, or change some of the assumptions used to combine the catalogue, and the leftover velocity changes too. That's why the reconstruction is statistical and map-like. No astronomer expects every galaxy to provide a flawless little arrow. They look for a broad pattern that survives the scatter, using enough measured distances that the collective motion becomes more persuasive than any single point. The answer remains somewhat sensitive to the catalogue and the model used to interpret it. That isn't a flaw being hidden. It's part of the measurement. There's something pleasantly humble about the method. A better camera alone would not have solved the mystery. The Great Attractor wasn't first recognized as a visible object posing for a portrait. It emerged from patient bookkeeping across the sky. Spectra, estimated distances, subtractions, uncertainties, and many small motions that seemed to lean the same way. Once those motion clues were assembled, where did their invisible arrows appear to point? Once you see how the method works, the strange history of the name starts to make more sense. The early maps didn't show a finished landscape. They were closer to weather maps drawn from drifting balloons. You could see which way the air was moving before you knew the shape of every mountain below. That doesn't mean astronomers were simply guessing. A guess can survive on one convenient clue. A reconstruction has to answer to hundreds, then thousands of measurements. Each galaxy contributes a small piece of motion. Most pieces are noisy, some disagree, but when enough of them bend into the same broad current, the pattern begins to deserve attention. Imagine a pencil map on a desk. At first, it holds only a few arrows. Then more arrows appear around them. Empty areas remain, and some arrows will later be corrected, but a regional shape is already forming. The landscape underneath is still only partly colored in. Even so, you can tell that the traffic is not wandering at random. That was the useful position astronomers found themselves in. They were reading currents before the coastline was fully charted. The attraction was visible first through motion, not through a complete census of everything producing it. The view was incomplete, but it was already useful enough to guide attention. That distinction changes the story. The Great Attractor is often described as though a huge structure was discovered, named, and then placed neatly on a map. The actual order was less neat. The motions came first. The map had to earn its details slowly. Those details depend on which galaxies have measured distances, where those galaxies lie, and how evenly the sky has been covered. Add a deeper catalogue, improve a distance estimate, or fill a neglected region, and the reconstructed flow can change. In 2023, Brent Tully and his colleagues used a much larger collection of galaxy distances to refine the surrounding flow field again. Revision wasn't an embarrassment. It was the method doing exactly what it should do when more of the sky becomes measurable. That also means no modern map should be treated as the last word on every boundary. Cosmic regions don't come with bright fences around them. Different reconstructions can shift an edge, alter a basin, or change how several neighboring structures appear to share the pull. The broad flow may be secure, while its precise geography remains open to improvement. There's a quiet reward in that kind of work. A catalogue can look like paperwork with a telescope attached. Yet patience turns rows of imperfect measurements into something you can almost watch moving. Not a photograph, exactly. More like a current made visible one arrow at a time. The famous old name belongs to an earlier moment in that process. Astronomers had found a direction in the flow before they had a satisfying view of what occupied it. Great Attractor named the pull that the measurements seemed to require. It did not begin as a label on a clearly outlined object. So by the late 1980s, the evidence had produced an awkward but productive situation. Galaxies across a large region appeared to be streaming toward the same part of the sky, while the source of that motion remained partly hidden and incompletely mapped. What then did astronomers think they had found? Names often make discoveries sound much tidier than they were at birth. Once you hear the Great Attractor, it's easy to imagine astronomers finding one enormous object, pointing a telescope at it, and giving it a suitably enormous name. That isn't how this one arrived. In 1987, a team led by Alan Dressler published evidence from the motions of galaxies across our part of the universe. The following year, Donald Lynden Bell and his colleagues pushed the case further. Their measurements suggested that many galaxies were being drawn toward the same broad area of the sky, in the direction of Centaurus and Norma. Imagine the result as a map covered with arrows. Each arrow belongs to a galaxy. They don't all point with perfect alignment, and they don't converge on one neat dot. Some tilt away, some carry more uncertainty than others, but enough of them lean toward the same broad region that the shared pattern becomes difficult to dismiss. It's a little like naming a weather system before you can see every cloud around it. You notice trees bending, pressure falling, and wind arriving from a consistent direction. Those clues don't show you the storm's complete shape. They do tell you that something organized is happening beyond the part you can see. For the astronomers, the organized thing was the flow of galaxies. The clue was dynamical. It came from motion, not from a clean photograph showing a single colossal object sitting at the center of everything. The phrase Great Attractor made the evidence sound almost comically decisive. Great Attractor. 2 words, both wearing very confident shoes, yet the early result was less like finding a hidden planet, and more like realizing that a wide landscape slopes downhill. You can watch loose objects roll in one direction long before you've mapped the entire valley. The proposed explanation was an overdense region. That simply means a part of space containing more matter than the cosmic average. More galaxies usually means more mass, along with matter that gives off little or no light. And more mass means a stronger gravitational effect on the surrounding region. This wasn't a claim that every moving galaxy was headed for one compact destination. Gravity works across a landscape. A broad concentration of matter can shape the motions around it without behaving like a single hook in space. The arrows were pointing toward a heavy neighborhood, not necessarily one address. But the name attached itself to the pattern before astronomers knew the region's modern shape, total mass, or exact boundaries. The late 1980s work did not hand them a finished portrait. It gave them a compelling direction and a gravitational demand. Enough matter had to lie somewhere toward Centaurus and Norma to help account for the motions they were measuring. That distinction changes the interpretation. The Great Attractor was not originally one clearly bounded thing waiting for a label. It was an inference about the nearby landscape of matter. The galaxies were behaving as though that landscape had a heavy, uneven rise in one broad direction, even while much of the terrain remained poorly seen. So the discovery was real in the way a current is real when you feel a boat drift. You may not know the full shape of the riverbed, you may not know which bend contributes most, but the motion is already telling you that the water isn't still. How then can a region be physically real before anyone can fully see it? Once a famous name overshoots, it's tempting to throw the whole thing away. If the Great Attractor isn't one enormous hidden object, perhaps there was never a Great Attractor at all. You don't have to make that jump. Think of a named neighborhood. The neighborhood can be real even if it isn't one building. It has streets, boundaries that soften at the edges, and a recognizable center. People may disagree about exactly where one district ends and another begins. That doesn't make the district imaginary. It means the name belongs to an area, not to a single address. The Great Attractor works better in that regional sense. It names a broad part of our cosmic neighborhood where matter is unusually concentrated and galaxy motions bend in a shared direction. The borders aren't crisp. On a map, you'd shade a swath of sky with a soft edge, not place one bright dot and declare the case closed. That softness doesn't mean anything goes. The region has a direction. It contains a genuine overdensity, meaning more matter than the cosmic average. And it has a historical connection to the pattern of motion that gave the name its purpose. Those are physical constraints, not decorative fog around an old story. In 1999, a large team led by Joachim Schmolt compared several surveys of nearby galaxy motion. Their work still treated the Great Attractor as a useful regional feature while examining how much of the local flow came from nearer matter and how much came from structures farther away. The name survived because the pattern it described survived. What changed was the neat idea that one dominant body, sitting at one simple location, explained everything. There are 3 different things here, and public explanations often slide between them. A region is the broad volume containing the excess matter and the related flow. A center is a chosen location used to describe that pattern. An object is a particular cluster, galaxy, or other bounded structure. Those words can point toward the same part of the sky without meaning the same thing. That distinction became even more useful in 2014, when Brent Tully and his colleagues mapped galaxy flows across a much larger volume and described our home supercluster, Laniakea. Their map widened the setting. The old regional pull became part of a larger network of matter and motion, with galaxies streaming through a landscape shaped by several concentrations and surrounding structures. This correction doesn't take the observation away. It gives the observation room to be as complicated as the universe that produced it. The Great Attractor can remain a real concentration within the local flow without becoming a lone cosmic monster. It can have a meaningful center without being one object at that center. And it can keep fuzzy borders without becoming a vague name for anything nearby. You've probably seen this happen with ordinary maps. A city label appears as one neat word, while the place itself spreads across suburbs, hills, rivers, and old boundaries that nobody can draw without an argument. The label is useful precisely because it compresses that mess. Trouble begins only when we mistake the printed name for a single building. So the soothing part is simple. Nothing real needs to be discarded. The galaxies still move. The concentration of matter is still there. The old name still points toward a scientifically meaningful region. We've only stopped asking it to behave like a photograph of one thing. If the name now describes a region rather than a monster, why has the monster version been so hard to let go? Some ideas survive because they're dramatically wrong. Others survive because they're only a little too neat. The Great Attractor belonged to that second group. The name did something useful at first. It gave people a way to talk about a broad pattern of motion without carrying the whole scientific argument into every sentence. But outside specialist conversations, the wording began to slide. Sometimes it meant a region of the sky. Sometimes it sounded like an object inside that region. Once a name becomes famous, those two meanings can quietly merge. You can see why. A region is difficult to hold in your mind. It has uncertain edges, several concentrations of matter, and motions that overlap across enormous distances. An object is easier. It sits somewhere, it pulls, it becomes the answer. You can almost put a pin in it. The mind does prefer one villain to a messy landscape. That doesn't make anyone foolish. A single cause simply feels complete. If several galaxies seem to be moving in roughly the same direction, it's natural to imagine one immense thing waiting at the end of their path. That view turns a complicated map into a simple story with a name you can remember. And there really was something missing from the map. Astronomers could measure the motion. They could trace its broad direction. But the part of the sky they most needed to examine wasn't easy to read. So the neat public image had room to settle in. A famous label hung over a partly hidden patch of sky, and the blank space beneath it invited something definite. When you can see the arrow but not clearly see what lies ahead of it, one destination feels almost unavoidable. Imagine hearing heavy furniture move in the apartment next door. You know the sound has a source, but you can't see through the wall. One table being dragged across the floor is an appealing answer. It's much less satisfying to imagine several people shifting chairs, boxes, and shelves at once. The simpler explanation may even point in roughly the right direction, while still getting the room wrong. That was the trap here. Public simplification took a real pattern and gave it a clean outline. A real observational blind spot then made that outline difficult to challenge. The one-object view hardened because nobody could simply point to a complete image and say, "There it is, and here are all its parts." The label was visible. Much of the landscape beneath it was not. The hidden sky doesn't explain every disagreement. Some of the ambiguity came from the motions themselves, and from deciding how much each concentration of matter contributed. Gravity across a crowded region doesn't leave neat fingerprints. Several structures can pull together, and their effects can be difficult to separate. Even with a clearer view, the answer was never going to reduce perfectly to one object. Still, the missing view mattered. Incomplete maps encourage complete stories. We fill the covered patch with whatever makes the rest of the view easiest to hold. And the obstruction wasn't some distant cloud placed conveniently between us and the answer. It was much closer, brighter, and more familiar. The sky we most needed to read lay behind the glowing band of our own galactic home. So how did the Milky Way manage to hide an enormous part of the universe from the astronomers standing inside it? There is something almost rude about the answer hiding behind our own front porch light. You might think a larger telescope would solve this. Point it toward the Great Attractor, gather more light, and look farther into the dark. That works when darkness is the problem. Here, the trouble is all the light, dust and stars already in front of us. A bigger view can simply give you a bigger view of the obstruction. Imagine an all-sky map with the Milky Way laid across it. From inside our galaxy, its disk appears as a bright, dusty band circling the sky. Unfortunately, that band crosses part of the direction astronomers needed to examine. It sits over the map like glare across a windshield, exactly where you're trying to see the road. The comparison only goes so far. Windshield glare mostly washes out what lies beyond it. The Milky Way interferes in two different ways. Dust between its stars absorbs and scatters visible light. Galaxies behind the dust look dimmer, redder, or disappear from an optical survey altogether. The farther you try to look, the more missing galaxies can distort the map you're building. Then there are the stars themselves. Near the galactic plane, so many crowd the image that picking out a distant galaxy becomes awkward. A background galaxy may be faint and fuzzy, surrounded by thousands of sharp foreground stars. Finding it can feel less like looking deeper and more like trying to recognize one quiet face in a packed stadium. Astronomers call this obscured strip the Zone of Avoidance. The name sounds as if the sky has marked out forbidden territory. It hasn't. It means optical galaxy surveys tended to avoid the region because their maps became less complete there, and an incomplete survey can make a genuinely crowded part of space look strangely empty. That mattered. In 1999, astronomers including Patrick Wood examined the hidden southern sky and described how the Milky Way's dust and crowded star fields interfered with searches for galaxies. In work from the same period, René Kraan-Korteweg and Wood showed why this was especially important near the Great Attractor direction. Part of the relevant region lay behind the very band where ordinary optical surveys struggled most. So this wasn't decorative astronomy trivia. It shaped what could be known. Astronomers could measure the motions of visible galaxies around the covered region and notice that those galaxies were being drawn towards something. Motion crossed the map as evidence. The mass responsible for that motion was harder to catalogue because many of its galaxies lay behind our own foreground. It's a peculiar arrangement. We live inside a spiral galaxy full of useful stars, including the one keeping us alive. Those same stars, along with lanes of local dust, clutter one of the sightlines we most want to clear. Our home gives us the observatory and blocks part of its window. None of this means the region was hidden at every wavelength. The Zone of Avoidance is mainly a warning about incomplete optical maps, not a claim that nature placed an absolute curtain across the sky. But once astronomers understood what the curtain was made of, they could choose ways of looking that dust and crowded starlight would hinder less. So what kind of light could pass through our galaxy's glare and begin filling in the missing map? The Zone of Avoidance sounds like a place you'd be wise not to enter. A forbidden district of the universe, perhaps, where galaxies disappear and sensible astronomers turn their telescopes elsewhere. The name has done rather well for itself. The technical meaning is much less theatrical. Avoidance describes what happened during surveys of galaxies beyond the Milky Way. Astronomers avoided trusting part of the sky because the view there became unreliable. The zone isn't a physical border, and it isn't an empty strip through space. It's the region where our maps begin losing objects because our own galaxy is sitting in front of them. Imagine a map of the entire sky flattened into an oval. Galaxies appear across it like scattered grains. Then, through the middle, their numbers suddenly thin out along a broad, dusty band. It can look as though the distant universe simply stops there. But the missing galaxies are mostly missing from the survey, not from space. That sounds like a small correction. On a map, though, it changes the meaning of the entire blank band. Along the plane of the Milky Way, light from distant galaxies has a difficult path to our telescopes. Clouds of dust absorb and scatter visible light. Gas adds more material to the foreground. Meanwhile, enormous numbers of stars crowd the same small patches of sky. A faint background galaxy can be dimmed, reddened, or lost among thousands of brighter points closer to home. By 1999, astronomers including Patrick Wood and René Kraan-Korteweg were describing how this combination of dust and crowded stars made optical searches sharply incomplete near the galactic plane. The closer a survey looked toward that band, the less confidently it could count what lay beyond. Survey completeness collapsed, even though the distant galaxies themselves carried on as usual. That distinction changes what the blank means. A blank area on a map feels like a fact about the territory. Sometimes it's only a fact about the map. And people are very good at giving blank spaces personalities. Old maps acquired sea monsters. This one acquired a name that sounds faintly ominous. When evidence for a huge concentration of mass appeared in roughly the same difficult direction, the Great Attractor inherited some of that atmosphere. Something powerful seemed to be pulling nearby galaxies, yet the ordinary visible map offered only a frustrating gap. The blind spot was real. The supernatural flavor was optional. It also wasn't complete blindness. Some galaxies could still be identified where the dust was thinner, where they were unusually bright, or where careful observations separated them from foreground stars. The zone had soft edges that changed with the survey, the telescope, and the kind of light being measured. There was no single cosmic boundary with avoidance written across it. One observer's nearly blank patch could be another instrument's difficult but usable field. That makes the name more precise without making the problem less interesting. Astronomers knew the map was incomplete, knew why it was incomplete, and knew an important part of the nearby universe might be concealed inside that incompleteness. The problem wasn't persuading the Milky Way to move, it was choosing a way to observe that could cope with the material in front of them. So if ordinary visible light struggled to cross that crowded, dusty foreground, what kind of light could reveal the galaxies behind it? A blank place on a map does something powerful to the imagination. Your eye doesn't like leaving it blank. It wants a mountain, an island, a creature in the sea, and when the map is of the nearby universe, one dark shape can begin to feel more satisfying than a crowd of half-seen galaxies. That's part of why the idea of one enormous hidden object had such staying power. It turned an unfinished view into a simple story. Something massive was concealed behind the Milky Way, and that one thing explained the motion around us. The name could change, the details could blur, but the shape of the story was wonderfully neat. The scientific position was less neat because the obstruction was real. Astronomers had good reason to be cautious about what lay beyond it. Their surveys were incomplete in a direction that mattered, and missing galaxies meant missing mass from their calculations. You couldn't simply look at the blank region, shrug, and declare it empty. But a justified gap in the evidence doesn't make every answer equally good. It only means the answer has to remain provisional. There's a difference between saying, something important may be hidden here, and saying, therefore one extraordinary object must be hiding here. The first respects the unfinished map. The second quietly finishes it with a marker pen. Still, you can see why that compression works. A large-scale flow produced by many galaxy groups, clusters, and more distant structures is hard to hold in your head. Their contributions overlap. Estimates change as surveys improve. Even experts may disagree about how much pull belongs to which part of the map. One unseen object is easier. It gives the uncertainty a location, a personality, and something that fits neatly into a headline. That doesn't mean the hidden sky caused every later disagreement. Astronomers also had to separate the influence of nearby structures from matter much farther away, and that problem remains difficult even with better observations. The gap helped the simple myth survive. It didn't create the whole scientific argument. You can watch the map begin to resist that myth in the work of Lister Staveley-Smith and colleagues. Their survey searched for neutral hydrogen, the cold atomic gas carried by many galaxies across the obscured southern sky. Instead of demanding a clean view in visible light, they listened for a radio signal that could pass through the foreground far more easily. Galaxies began appearing where older maps had looked thin. That survey didn't uncover a single dark monarch sitting behind the Milky Way. It recovered pieces of structure, galaxies gathered into groups, chains, walls, and concentrations. The blank space became busy, not perfectly known, and certainly not simple, but increasingly populated by ordinary cosmic architecture. There's something quietly relieving about that. The answer wasn't a magical object waiting behind a curtain. It was that the curtain had favored certain instruments and frustrated others. Change the instrument, and the unfinished map starts giving some of its territory back. Radio measurements were only part of that recovery. Infrared surveys could find other galaxies through the dust. X-ray observations could reveal hot gas in massive clusters. Each wavelength noticed something the others missed, like several people describing the same dark room by touch, sound, and faint warmth. So what happens to the hidden sky when astronomers stop asking visible light to do all the work? The clever part of astronomy is often not seeing farther, but seeing differently. Imagine trying to understand a room filled with smoke. Night vision might reveal the warm outline of a person, but it won't show you every chair, every wall, or the cold glass on a table. You need several senses, and each one gives you a different piece of the room. Near-infrared surveys offered something like night vision. Infrared light passes through much of the dust that blocks visible light, so galaxies hidden behind the Milky Way began to appear. That was a major improvement. It was also tempting to think the problem had become straightforward. Scan the hidden strip in infrared, count what appears, and fill in the map. But dust wasn't the only obstacle. Crowded fields of foreground stars could still make galaxies difficult to identify. Some galaxies were easier to detect than others, and infrared surveys traced starlight, which meant they favored objects bright enough in the right part of the spectrum. The recovered sky was clearer, but it wasn't complete. Radio astronomers approached the same region by listening for neutral hydrogen. Astronomers call it HI, ordinary hydrogen atoms carrying a radio signature at a very specific wavelength. That signal travels through the Milky Way's dust with little trouble. A galaxy rich in hydrogen can announce itself in radio, even when its stars are buried behind the crowded foreground. Surveys led by astronomers, including Lister Staveley-Smith, used that signal to search the Zone of Avoidance. The observations found gas-rich galaxies that optical surveys had missed. Better still, the radio signal shifted with the galaxy's motion, so it gave astronomers a rough distance clue as well as a detection. A hidden dot could become part of a three-dimensional pattern. There was a catch. Galaxies poor in neutral hydrogen could remain quiet. Large elliptical galaxies, especially those gathered near the centers of rich clusters, often contain less cold hydrogen than spiral galaxies do. Radio could find one population beautifully while barely noticing another. The room was still being rebuilt from partial impressions. That's where X-ray observations helped. Massive galaxy clusters hold enormous clouds of gas heated to millions of degrees. That gas shines in X-rays, so even when the individual galaxies were hard to separate behind the Milky Way, the hot atmosphere around an entire cluster could reveal that something large was there. X-ray surveys were especially useful for finding the dense environments that hydrogen searches could undercount. Then redshift surveys added depth. Astronomers measured how much a galaxy's light had been stretched as the universe expanded. Galaxies that looked close together on the sky could be separated by vast distances. Others could be placed into the same wall, filament, or cluster. The flat patchwork slowly became a map with structure. No single survey ended the problem. Coverage differed from one part of the sky to another. Sensitivity varied. Each method selected its own kind of object and missed something else. The solution was cumulative: infrared for hidden starlight, radio for hydrogen-rich galaxies, X-rays for hot cluster gas, and redshifts for distance. It's a quietly ingenious way to work. Astronomers didn't remove the Milky Way or make the dust disappear. They let several imperfect instruments disagree usefully, then combined what each could recover. Once those fragments were fitted together, what kind of structure began to emerge behind our galaxy? Once the dust starts to thin, the surprise isn't one brilliant object waiting in the dark, it's a pattern. A galaxy appears here, another there, then a cluster farther along. At first, they look like scattered finds, but when astronomers add their distances, those points begin to line up. Imagine watching a coastline emerge on radar through heavy rain. One return might be a ship. 3 might be coincidence. Then the returns trace the same curve for hundreds of miles, and the shape becomes hard to dismiss. The analogy only goes so far. Galaxies aren't fixed pieces of shoreline, and their full three-dimensional positions matter. Still, the useful part holds. Separate detections become more convincing when they join into something continuous. That happened in the southern zone of avoidance. In 1999, astronomer Patrick Wood and his colleagues reported mapping that helped reveal coherent large-scale structure behind the Milky Way's foreground. The recovered galaxies weren't merely a collection of curiosities. They belonged to a wider arrangement of clusters, walls, and connected concentrations stretching across the obscured sky. Imagine the old map as a row of bright points with too much darkness between them. As more measurements arrive, the points don't just multiply. They resolve into a broad, wall-like band, with clusters embedded inside it. A detection made in one survey gains weight when another survey finds the structure continuing nearby. Add distance measurements, and some apparent neighbors turn out to be unrelated. Others fall into place along the same enormous feature. The hidden region begins to feel less like a mythical place where something enormous might be lurking, and more like buried geography. There's a quiet satisfaction in that change. A stubborn blank on the map acquires edges, depth, and connections. The answer becomes less mythical and more cartographic. Looking for one single object encourages you to treat the Milky Way's blind spot like a curtain hiding a single piece of furniture. The mapping showed that the curtain covered part of the room. What lay behind it had extent, direction, and relationships. It joined the structure already visible on either side. The foreground had interrupted our view, not the structure itself. For the first time, you can almost feel this missing region under your feet. It isn't a vague pull from somewhere beyond the stars. It's part of the same cosmic landscape we inhabit. Galaxies aren't sprinkled independently through space. Gravity gathers them into groups and clusters, while those clusters sit within filaments and broad walls around emptier regions. The obscured southern sky belonged to that architecture too. Connected structure doesn't mean the accounting was finished. A map of galaxies is not automatically a complete map of mass. Some galaxies remain undetected. Gas and dark matter contribute without announcing themselves in ordinary starlight. And even when a broad feature is visible, astronomers still have to work out which parts contribute most strongly to the motion of our local galaxies. But the blank patch had changed. It now contained a region rather than a rumor. Instead of asking whether one hidden monster explained everything, astronomers could ask how the mass was spread across a connected landscape. A landscape, though, still needs landmarks. Within that newly recovered wall of structure, which place would become the one astronomers could point to by name? Even after a map starts to appear, it's tempting to treat it like a finished photograph. The hidden region has been recovered. The shapes are there. Surely everything left is just a matter of sharpening the view. But this map was never a single view. Imagine trying to recover a coastline from several imperfect scans. One catches the broad curve of the shore. Another picks up rocky headlands but misses the beaches. A third sees the shallow water just offshore. None is complete, yet the places where they agree begin to hold still. The coastline becomes credible because its separate outlines keep meeting in the same places. The hidden sky worked much the same way. Different wavelengths responded to different traces of matter. Each view picked out something the others handled less well. Astronomers could stack those transparent layers, compare them, and watch a stable landscape emerge where the Milky Way had once left an awkward blank. Confidence came from that overlap. A concentration seen in one survey might be uncertain. A concentration that returned in independent observations using different tracers was much harder to dismiss. The surveys didn't have to match perfectly. In fact, they couldn't. They were sensing different parts of the same region. What mattered was that their larger shapes supported one another. No single survey ended the hidden sky problem. There was no final exposure that made the Milky Way politely step aside. Some areas remained harder to read than others. Distances carried uncertainty. The distribution of mass still had to be inferred from the things instruments could detect. That doesn't make the recovered map flimsy. it makes it assembled. Its strength came from several partial views surviving comparison with one another. Every agreement tightened the outline a little more. Every mismatch showed astronomers where the map still needed work. You probably know this kind of confidence from ordinary life. If several people describe the same street from different windows, their accounts won't be identical. One notices the traffic, another sees the buildings, someone higher up can follow the road beyond the corner. Put those partial views together, and you can understand the neighborhood without pretending that anyone saw all of it. That was the achievement here. The blank region became a persuasive physical landscape. Its broad connections could be followed, its dense areas could be compared, and its place within the motion of nearby galaxies could be tested with something firmer than a guess. A credible map is not the same thing as a final map. It can still contain blurred edges, missing pieces, and disputed weights. Yet it gives astronomers enough structure to stop arguing about an empty patch and start examining particular features inside it. The uncertainty now had a shape. That alone made it much easier to investigate. One feature stood out especially well. Rich, dense, and placed close to the direction associated with the Great Attractor. It offered something unusually useful, a landmark that could be studied and named. It didn't replace the larger region, and it didn't become the entire explanation. A city can dominate a map without becoming the whole country. By then, the fog had thinned. The recovered landscape was broad enough to keep any one object in perspective, but clear enough for a major cluster to step forward. So why did the Norma cluster become the landmark astronomers kept returning to? The name is ACO 3627, though the easier name to keep is the Norma cluster. After years of tracing a broad disturbance through a part of the sky buried behind the Milky Way, astronomers finally had one solid place to point at. That changed the feeling of the search. A hidden region can remain slippery even after its outline appears on a map. Norma was different. It was a real cluster of galaxies, rich and massive, sitting near the heart of the region historically called the Great Attractor. The hidden sky had finally given up a proper noun. Imagine a mountain ridge blocking your view of a distant city. At first, you notice only clues, a glow above the ridge, roads bending towards something unseen. Then you find a gap and catch sight of the city center. You haven't seen the whole landscape, but one dense concentration suddenly makes the map much easier to understand. A galaxy cluster works a little like that city center. Hundreds of galaxies occupy the same general neighborhood, along with hot gas and a much larger amount of dark matter. Each galaxy is massive on its own. Gather many of them together, and you have a substantial knot of mass within the wider cosmic landscape. Clusters also give astronomers several kinds of evidence in one place. The galaxies mark the concentration, hot gas reveals its depth, and the motions inside it hint at mass no telescope can see directly. That was why Norma deserved attention. It wasn't merely another galaxy appearing through the dust. It was the sort of structure that could help explain why this part of space had stood out in measurements of motion and density. In 1999, astronomers René Kraan-Korteweg and Patrick Wood described ACO 3627 as a nearby rich cluster in the Great Attractor region. Their work helped establish Norma as one of the strongest known concentrations there. Other mapping, led by Wood that same year, placed the cluster within a larger wall-like arrangement of galaxies, tying this newly visible landmark back to the broader structure that surveys had been recovering behind the Milky Way. So the view wasn't of one lonely cluster sitting in otherwise empty space. Norma belonged to a wider overdense environment. It was the clearest city center in a landscape that also contained suburbs, roads, and other concentrations extending beyond it. That distinction is important because a named object is almost too convenient. Once Norma appeared in roughly the right direction, it was tempting to let the whole Great Attractor story collapse into this one cluster. There it is, mystery solved. Astronomers are not immune to the relief of finally having something that fits neatly on a label. But the historical Great Attractor was a region inferred from the motions of galaxies across a much broader volume. Norma gave that region a convincing landmark, It didn't prove that all the surrounding motion came from Norma alone, and it didn't provide a final accounting of how much of our local group's motion belonged to this one cluster. Still, the discovery was a genuine step forward. An invisible pull had become connected to a visible concentration of galaxies. The thing behind the dusty ridge now had streets, lights, and enough mass to take seriously. Norma had made the hidden region feel real. But was this enormous cluster actually enough to explain the pull by itself? One clear landmark always tempts the mind into one clear culprit. Find the biggest cluster near the center of the pull, and the old Great Attractor story seems ready to snap back into place. Norma did it, case closed. But a cluster can be enormously important and still belong to something larger. Think of the brightest downtown you know. From a distance, its towers dominate the view. They mark the busiest part of the map, and they tell you where a great deal of activity is concentrated. Yet downtown isn't a city floating by itself. Roads feed into it, neighborhoods spread around it, other centers sit beyond it. The skyline is a useful landmark, but it doesn't contain the whole city. Norma sits in its hidden region much like that. Its galaxies gather an extraordinary amount of mass into one place, making the cluster a major local source of gravity. But the same surveys that brought Norma into view also recovered a wider pattern around it. Galaxies weren't scattered randomly behind the Milky Way's dust. They traced a broad wall and a connected environment of groups and clusters, with Norma appearing as one particularly bright knot inside it. In 1999, Patrick Woot and his colleagues reported results from surveys of the obscured southern sky. Their map placed the Norma cluster within that larger arrangement. The hidden region already had structure before one landmark became memorable enough to stand in for all of it. Norma was a major node in the structure, not a solitary weight sitting in otherwise empty space. That distinction is important because gravity doesn't respect the labels we put on a map. A galaxy near Norma responds to the cluster, but it also responds to mass spread along the surrounding wall and to structures farther away. Those pulls overlap. By the time we measure the motion of our own local group, they arrive bundled together. Trying to assign an exact share to Norma alone becomes awkward, especially when part of the sky remains difficult to survey evenly. There still isn't a neat gravitational receipt with every contribution printed on its own line. This is where a map is safer than a villain. A villain gives you one name and one cause. A map allows several concentrations of matter to pull at once, across different distances and scales. It's less neat, but the universe was under no obligation to arrange its gravity for a clean ending. Later work kept that restraint. In 2006, Christoph Bolejko and Charles Hellaby examined how structures on different scales contribute to the cosmic motions we observe. Their analysis gave no comfortable reason to stop at a single nearby cluster. The surrounding region contributes too. So does the question of whether the calculated motion settles toward the measured value as larger volumes are included. Norma therefore remains one of the most important pieces of the old Great Attractor region. Calling it incidental would ignore the concentration of mass sitting there. Calling it the entire explanation would make the opposite mistake. The bright knot belongs to a wall. The wall belongs to a wider landscape, and our motion records the combined pull of that landscape. So when the map expands beyond Norma and its neighboring structures, does the predicted motion finally match the one we actually measure? A landmark can make a map readable without being the whole destination. Think of a lighthouse seen from a dark coast. Once you spot it, you know where you are. You can point to something solid. But the lighthouse doesn't explain the shape of the entire shoreline. Norma did something similar for the Great Attractor. It gave astronomers a clear concentration of mass in the part of the sky that had been so difficult to inspect. That was a major advance. The old view of one hidden monster pulling everything toward itself could finally be replaced with something that could be mapped, measured, and tested. And testing changes the question. At first, the question was simply, what is there? Once Norma became visible, astronomers could ask something stricter. Is that enough? Does the gravity associated with this nearby structure account for the whole motion of the local group, including the speed and direction we observe? The answer was no. Norma contributes enormously, but Norma alone doesn't account for all of that motion. The cleanest wording is also the most useful: landmark, not culprit. That distinction can feel slightly unsatisfying. You spend years trying to see through the Milky Way, find a massive cluster in roughly the right direction, and then discover that the arrows on the map keep going. Science can be awkward like that. The object you worked so hard to uncover turns out to be a proper answer to one question, and only part of the answer to the next. But this wasn't a retreat from the discovery. It made the discovery useful in a more demanding way. Once a nearby concentration had been identified, researchers could calculate how much motion it should produce. They could then compare that prediction with the dipole, the large directional pattern seen in our motion relative to the cosmic background. If the numbers and directions settled as more nearby matter entered the calculation, then the pull might be said to converge. If they didn't, the map still wasn't wide enough. In 2006, Pirin Erdogdu and colleagues used galaxy survey data to examine that very problem. They weren't merely hunting for another impressive object. They were asking whether the pull inferred from the mapped nearby universe fully converged toward the dipole we observe. That is a tougher standard than finding a large cluster in the expected part of the sky. A landmark tells you where an important mass lies. Convergence asks whether the mass you've counted is sufficient. So Norma made the nearby part of the case visible enough to test. It did not close the case, nor should we shrink it into a footnote simply because the motion has additional causes. A large contributor can still be incomplete. Your heater may warm most of a room, while a cold window continues to shape the temperature beside your chair. Both facts can be true without either one becoming trivial. This is where the Great Attractor story grew up a little. The goal was no longer to name the hidden object and go home. It was to measure how the predicted pull changed as the survey widened, and to see whether those continuing arrows finally came to rest. If Norma is the landmark, how far beyond it must the map extend before the motion truly converges? Imagine drawing one arrow on a clear sheet of plastic. It points toward the pull predicted by the matter in our nearby cosmic neighborhood. Then you lay another sheet over it, adding galaxies from farther away. The arrow shifts. Add another layer and it shifts again. At some distance, you hope the new layers barely matter. The arrow has settled. That settling is what astronomers mean by convergence. How far out must you count the surrounding structure before its combined gravitational pull stops changing very much? If the arrow settles after the nearby concentrations are included, then the local map may be enough. If it keeps turning or growing as the survey reaches outward, more distant structure is still contributing to the motion. This changes the question in a useful way. Asking which concentration is biggest can give you a famous place name. Asking whether the predicted pull is enough gives you a measurement you can test. In 2006, Pirin Erdogdu and colleagues used a large survey of galaxies selected in infrared light to study this problem. They compared the accumulated pull inferred from the galaxy distribution with the dipole we observe in our own motion. Nearby overdensities mattered, but the point of the work was to keep widening the count and watch what happened, rather than declare victory when one impressive concentration appeared. Think of estimating which way a crowded table will tip. You begin with the heavy objects near the center. Then you include a stack of books near one edge, a bowl farther away, and someone's elbow resting rather unhelpfully in the corner. Each addition changes the combined effect. You stop only when adding more of the table no longer changes your answer by much. A galaxy survey does something similar across an enormous volume. As its depth increases, astronomers add more of the uneven cosmic landscape. They calculate the cumulative pull again and see whether the predicted arrow has stabilized. The important curve is not simply how much matter has been counted. It is how the direction and strength of the accumulated pull behave as the boundary moves outward. And the boundary changes the result. Different surveys select galaxies in different ways. They cover the sky differently, reach to different depths, and require different corrections, so different datasets can make convergence appear at different scales. That isn't science becoming vague, it is science becoming more exact about what each map can support. You wouldn't expect 2 photographs taken through different filters to reveal every feature at the same moment. One may bring nearby dusty galaxies into view especially well. Another may represent a different population or sample the distant landscape more completely. If their cumulative arrows settle differently, that difference has to be examined, not polished away. So there is no single distance that every analysis has agreed upon. Some studies find much of the observed motion accounted for relatively nearby. Others leave room for contributions from farther out. Norma remains important in either case. The sharper claim is simply that importance and completeness are separate things. That distinction opens the map. The motion can be shaped by a broad gravitational landscape rather than one dominant destination, with each widening survey testing how much of that landscape has finally been included. If the arrow is still changing after the Great Attractor region is counted, what farther structures are helping to turn it? The frustrating and beautiful part of real science is that a powerful clue can be genuine without being complete. Finding the Great Attractor region changed the story. It showed that the motion of our galaxy and its neighbors wasn't random, but a real influence doesn't have to be the only influence. Imagine rainwater running down a hillside. A nearby ridge can bend the stream sharply. You could stand beside that bend, trace the slope, and correctly identify what turned the water. Then you could follow the stream farther and notice that its overall path still depends on hills beyond the ridge. The first answer wasn't worthless. It just wasn't the whole landscape. Gravity works across its own kind of landscape. Galaxies gather into groups, groups into clusters, and clusters into much larger concentrations. Each patch of extra mass adds a pull. The nearby concentration around the Great Attractor can strongly shape the local flow without using up every contribution to it. Important and enough are 2 different claims. Scale can be slippery here. We're used to looking for the nearest large object and assigning it most of the blame. Gravity doesn't respect that neat habit. Many smaller or more distant concentrations can add together, and their combined influence may tilt the motion even when none looks like the obvious answer by itself. That difference became harder to ignore as surveys grew. In 1999, a team led by Ian Schmolt compared the motion of our local group with the pull inferred from galaxies mapped by the IRAS satellite. Their analysis left a substantial role for structure on scales larger than the nearest overdense region. They weren't erasing the Great Attractor from the map. They were saying the map had to extend farther. In 2006, Pairen Erdogdu and colleagues used the 2-micron all-sky survey to reconstruct the density and motion of the nearby universe. Infrared light helped them trace galaxies through regions where dust in the Milky Way makes ordinary observations difficult. Again, nearby overdensities mattered. Again, they didn't explain everything cleanly by themselves. It's tempting to ask for a neat number. How much belongs to the nearby region and how much belongs farther away? The evidence doesn't support one universal percentage. Different surveys cover different depths. They weigh galaxies in different ways. They also have to estimate mass from the light they can see, while accounting for the parts of the sky that remain difficult to map. A precise-looking fraction would hide those choices instead of settling them. A river offers another useful view. The nearest bend in the bank may turn the current beneath your feet, but the wider course of the river still reflects the valley ahead. In much the same way, gravitational influence accumulates across scales. A nearby node can dominate one part of the motion, while a broader distribution of matter helps set its final direction. So the name Great Attractor still points to a real region and a real piece of the flow. What changed was the idea of a single culprit. The motion began to look less like galaxies falling toward one concealed object, and more like galaxies responding to a landscape of mass, some near and some much farther away. And once astronomers widened the map, one distant concentration kept becoming harder to leave out: the enormous Shapley concentration. How much of our motion begins to make sense when Shapley enters the view? A wider answer can sound like no answer at all. If there isn't one hidden object doing the pulling, perhaps astronomers have simply replaced a clear mystery with a cloud of possibilities, a bit of cosmic hand-waving only spread across a larger map. But the wider map has shape. Imagine a relief map after a rainstorm. Water doesn't choose one destination point because one deep hole commands the entire landscape. It runs down slopes, gathers into channels, joins other streams, and settles within broad drainage basins. A nearby hollow can bend the water sharply. A distant valley can help determine where the whole system is going. You need the shape of the ground to understand the route. The modern view of galaxy motion works in a similar way, though the thing moving isn't water. It is matter responding to gravity across the uneven structure of the universe. Astronomers estimate those motions by comparing where galaxies appear to be going with the motion expected from cosmic expansion alone. The difference reveals a flow field. Galaxies form streams. Neighboring streams gather into larger patterns. Those patterns can be grouped into basins, where motion tends to converge through the surrounding cosmic network. This doesn't mean every galaxy follows a neat painted line. The map is a reconstruction built from many measured motions. Some paths are clearer than others. The key point is that the motions aren't scattered at random. Across large regions, they share directions, curve together, and separate along recognizable boundaries. These aren't decorative names placed over a vague map. In 2023, Brent Tully and his colleagues used measured galaxy motions to trace this landscape across our part of the universe. Their map contains identifiable structures, boundaries, and directions of flow. It shows which galaxies appear to travel together and where neighboring flows begin to part. That makes the answer larger, but also cleaner. We no longer have to force every motion into a single arrow aimed at a single dot. We can ask which nearby structures bend the flow, which larger concentrations help set its direction, and how the filaments and emptier regions between them shape the route. The emptier regions matter because gravity is about imbalance. A galaxy can be drawn toward a dense region while also moving away, in a relative sense, from a neighboring void where there is less matter pulling back. Add several dense regions, several voids, and the geometry connecting them, and the final motion belongs to the whole arrangement. You can feel why the old view became too small. One destination point asks one place to explain motion spread across an enormous, lopsided network. The relief map allows several influences to act at once without turning them into a random list. Positions, masses, and measured streams all affect the result. So does the way the cosmic network places one influence beside another. There is still uncertainty in the map. Distance measurements carry errors, and some matter remains difficult to trace. Basin boundaries can shift as observations improve. A stream near an edge may be assigned differently when better data arrive. But uncertainty about the edges doesn't erase the flow itself. It shows astronomers where the map is still being sharpened. So the search has changed. Instead of asking where the culprit is hiding, astronomers can ask what arrangement of matter produces the motion they measure. And when they follow that arrangement beyond the nearby basin, the map brings a much richer, farther structure into view. How does that larger concentration change the flow? Once the map widens, one name keeps looming larger in the distance: Shapley. Imagine the local flow map as a landscape seen through a narrow window. The Great Attractor is the first large ridge you notice. It's nearby enough, in cosmic terms, to bend the paths around it. Open the window farther, though, and another rise enters the frame beyond that first ridge. It's broader, richer, and packed with an extraordinary amount of matter. This is the Shapley concentration, often called the Shapley supercluster. It lies far beyond the Great Attractor, in roughly the same general direction across our sky. Within it are thousands of galaxies gathered into many clusters, with more matter spread through the space between them. It's one of the richest mass concentrations in our nearby part of the universe. Nearby is doing a heroic amount of work there. Shapley is hundreds of millions of light years away. The light reaching us tonight began traveling long before our species existed. Yet, on the scale of the observable universe, it still belongs to our wider cosmic neighborhood. In 2006, cosmologists Christoph Bolejko and Charles Helleby examined how structures on these larger scales contribute to the motions we measure closer to home. Their work placed Shapley where any serious account of the surrounding flow has to place it, inside the discussion, not beyond the edge of the map. That is a long reach, but not a license to call Shapley the answer. The tempting response is to swap one answer for another. Perhaps astronomers blamed the Great Attractor, then discovered the real cause was Shapley, nice and neat, also too simple. A farther ridge can bend a watershed without erasing the nearer ridge. Water crossing a hillside responds to the whole shape beneath it. A small rise close by may turn the stream sharply. A much larger rise farther away may tilt the broader route. Neither has to act alone, and naming the larger one doesn't make the closer one imaginary. Gravity works through that larger landscape. Shapley's enormous concentration of matter can help shape the cumulative flow across a vast region. But astronomers can't assign it some neat final percentage of the local group's motion. The distance measurements aren't perfect. The surrounding matter isn't mapped without gaps, and the flow we observe is produced by many structures, including dense regions that pull and emptier regions that leave less resistance on the other side. So Shapley enlarges the old answer. It doesn't merely replace it. The Great Attractor still points to a real nearer region where the local flow gathers. Shapley shows why stopping there makes the explanation too small. That distinction changes the search. A structure can be important without being the only cause. It can even be enormous without being cleanly dominant in every measurement. Once Shapley enters the frame, the search no longer resembles a hunt for one hidden object. It becomes an attempt to weigh several parts of one uneven cosmic landscape. And now the map has reached its widest scale so far. The nearby ridge remains beneath us. Shapley rises much farther out. Between them sit other clusters, filaments and large empty regions, all contributing to the slope we're moving across. So how do astronomers decide which parts of that landscape are merely important and which ones truly dominate the motion? The mind still wants a winner. Give it two enormous structures, and it immediately asks which one is really in charge. Shapley is farther away and much larger, so it can feel like the grown-up answer replacing an earlier, smaller mistake. The Great Attractor was only a clue. Shapley must be the destination. Case closed. But size alone doesn't settle how much a structure contributes to our motion. Imagine rain falling across a broad watershed. One ridge may turn the water near your feet. Another, much larger ridge may bend the land farther away. Both help shape the route. Neither ridge has to control the whole flow by itself. And measuring the water at one point won't tell you what every ridge contributes everywhere else. Galaxy flows work in a similar way. Matter changes the gravitational slope across space. A nearby concentration can strongly affect one part of that slope, while a farther concentration adds another pull across a wider region. These influences overlap. They don't arrive with neat labels attached, and they certainly don't take turns. Important is not dominant. That distinction may sound small, but it keeps the wider map from becoming another one-object myth. In 2006, cosmologists Christoph Bolejko and Charles Hellaby studied models of the large-scale flows around us. In some of their results, Shapley made only a limited direct contribution to the local group's motion. That doesn't make Shapley irrelevant. It means the answer depends on the model, the region being measured, and how the surrounding mass is represented. It's tempting to turn that into a neat percentage. Shapley provides this much, the nearer structures provide that much, and the remaining motion goes into a convenient little box. But without the exact setting of a particular paper, those numbers can mislead, change the assumptions or the volume being studied, and the shares can change too. The cleaner statement is also more accurate. Shapley helps explain why the old Great Attractor only story was incomplete. That may feel less satisfying than naming a single cosmic boss. Distributed causes are emotionally untidy. We are comfortable with one hand pulling a rope. We're less comfortable when the rope crosses a landscape, turns around several bends, and disappears behind terrain we can't fully see. Unfortunately, gravity has never shown much concern for our preference for simple suspects. Still, A distributed answer isn't a weaker answer. It's a better description of what gravity does across an uneven universe. The nearer structures remain part of the motion. Shapley contributes on the farther scale. Other clusters and filaments help shape the flow between them. Even under-dense regions affect the balance, because having less mass on one side changes it just as surely as having more mass on the other. So the Great Attractor hasn't vanished from the story. The name still points to a real feature in the flow around us, even after the map widens beyond it. What has vanished is the hope that one object can carry the entire explanation. The title stays accurate. There is an attraction in this part of the sky. It just belongs to a landscape, not a lone destination. The mature view looks more like those two ridges bending one watershed. You can't understand the water by choosing your favorite ridge. You need a map that keeps nearby and distant influences in view without pretending either one is the final stop. What kind of map can hold all of that motion at once? A list of names can feel like progress. You place one pin on the map, then another farther away. Each pin marks something real, but after a while, the map begins to resemble a detective's wall covered in photographs and string, busy, impressive, and still missing the explanation. We've reached that point here. The scale has grown beyond one concentration of galaxies, and the old language is starting to strain. If several structures help shape the motion, naming each of them won't tell you how their effects fit together. A longer suspect list is still a suspect list. It gives you more candidates to remember, but no better way to understand their relationship. So we can leave behind the search for one winner. Imagine taking down all those separate pins and unfolding a map of ridges and valleys. Pour rain across it, and the water doesn't care which hill has the most memorable name. Each drop follows the slope beneath it. A nearby rise turns it one way. The broader terrain may bend its route again. The shape of the landscape decides where neighboring paths gather and where they separate. Galaxy motions can be mapped in a related way. Instead of treating every large structure as an isolated object tugging from its own labeled spot, you follow the measured flow. You ask which trajectories come together, which ones peel apart, and where the dividing lines lie. Those lines work rather like watersheds on Earth. Rain falling on opposite sides of a ridge may end up in different rivers, even when the drops began only a few feet apart. This doesn't make the galaxies behave like water. The comparison gives us a cleaner way to organize their motion. It lets a map include several influences without forcing them into a contest that only one can win. The ridge affects the path. The valley does too. So does the direction the ground keeps sending everything that crosses it. That changes what the map is for. You're no longer pointing at the most powerful looking feature and declaring the case solved. You're describing the pattern made by many motions at once. Clusters, filaments, and broad concentrations of matter don't disappear. They take their places inside a connected landscape where their effects can be understood through the paths around them. And rather usefully, that larger view can be easier to hold in your head. A dozen labeled attractions leave you asking which one outranks the others. A basin shows how several structures can belong to the same pattern. The answer becomes simpler because the map carries the relationships for you. In 2014, Brent Tully and his colleagues used this kind of flow-based thinking to redraw our place in the nearby universe. They weren't merely adding another grand object to an already crowded chart. They changed the rule used to draw the boundaries. The motions of galaxies, rather than the fame of any single structure, would show which regions belonged together. We'll leave the full shape of that map untouched for the moment. Its boundaries need room to arrive clearly. But notice what had to happen before anyone could draw it. The view had to widen beyond the first ridge. The hope for a lone culprit had to fade, and isolated attractors had to give way to trajectories, dividing lines, and shared flow. The explanation hasn't become a longer list. It has become a different kind of map. That map was given a name, Laniakea. So what exactly did Laniakea change? Sometimes the better answer is not a new object, but a new way of drawing the map. We're used to maps with edges. A country ends at a border. A lake ends at its shore. So when astronomers describe an enormous gathering of galaxies, it feels natural to look for some visible outer wall. Galaxies on this side belong together. Galaxies on the other side do not. But gravity rarely gives us such neat inclines. At these scales, the old question was asking for a pin on the map when the answer wanted a contour map. Instead of asking where a structure stops, you ask where the motion changes direction. Imagine rain falling across a broad landscape. 2 drops may land only a few inches apart, yet take very different paths. One runs toward a river to the east, the other slips west into another valley. The ridge between them is a watershed. You don't decide which drainage basin a drop belongs to by measuring its distance from the nearest town. You follow the slope and watch where the water goes. A basin of attraction applies a similar idea to galaxies. The landscape isn't made of soil and rock, and the galaxies aren't visibly rolling downhill. There's no cosmic hillside for you to see. Astronomers have to reconstruct the hidden gravitational terrain from the galaxy's motions. They begin with the general expansion of the universe. Most galaxies are being carried apart as space expands. Then astronomers look for the extra motion each galaxy has relative to that expansion. That extra motion is called peculiar velocity, though there's nothing especially peculiar about it. It's simply the local pull of gravity showing through the broader outward flow. One measurement tells you very little. Gather enough of them, though, and the motions begin to form flow lines across the map. Some streams of galaxies converge toward the same region. Other streams turn away and join a different flow. The dividing surfaces between those patterns act like cosmic watersheds. They separate one basin of attraction from the next, even when no bright edge appears in a telescope. That changes what belonging means. A galaxy belongs to a basin because its reconstructed flow joins that basin's larger pattern. The boundary comes from motion, not appearance. It's closer to a map of where the traffic is going than a photograph of where the headlights happen to be. The galaxies don't need to sit inside a neat, visible box. Their paths supply the boundary the view cannot. And the map has limits. These flows are reconstructed from incomplete measurements, so the details can change as better data arrive. A galaxy inside a basin is not necessarily tied there forever. The universe keeps expanding, nearby masses keep pulling, and the largest regions may not be permanently bound as one object. A watershed describes the present flow field. It isn't a fence bolted into space. Without that distinction, a newly named region can sound like someone has simply placed a grand label around an especially crowded patch of sky. In 2014, Brent Tully and his colleagues did something more careful. They used galaxy motions to trace an immense basin whose flow lines converged into a shared pattern. The result became the best-known example of this map upgrade, Laniakea. So what shape appears when the galaxies around us are redrawn as streams within that basin? Once you hear the name Laniakea, it's easy to imagine something solid and monumental. A structure with an outer wall, perhaps, and all the galaxies inside it belonging together. The name feels as though it should appear in enormous letters across a map, but Laniakea is less like a box drawn around part of the universe and more like a basin revealed by motion. Astronomers reached it by reconstructing how galaxies and galaxy groups move after the general expansion of the universe is taken into account. Each measured motion adds a small clue. Put enough clues together and streamlines begin to appear. Those lines show which way matter in a region is flowing under the combined pull of nearby concentrations of mass. Galaxies whose reconstructed paths converge within the same broad flow pattern are assigned to the same basin of attraction. That basin is Laniakea. Its boundary isn't a bright shell floating in space. You couldn't fly toward it and watch a line pass over your windshield. The edge appears on the map where the flow divides, with galaxies on opposite sides tending toward different basins. It's a border made from directions, which is a slightly odd thing to call an edge, but a useful one. That makes the answer better, rather than merely bigger. Laniakea gives astronomers a way to describe relationships among motions that once looked like separate local puzzles. It connects our galaxy's movement with the movements of neighboring groups and clusters across a much larger region. The name belongs to the pattern those motions make together, not to a colossal object wrapped around them. And the scale is difficult to hold in your head. Laniakea is commonly described as about 500 million light-years across. That's about 4.7 quintillion kilometers. Light leaving one side would need about 500 million years to reach the other. When that light began traveling, complex animals had barely started becoming common in Earth's oceans. The basin is so wide that human history doesn't make a useful measuring stick. Even the history of our species disappears completely inside the crossing time. Yet the Great Attractor hasn't been erased by this larger view. It still names the region of concentrated mass associated with a major part of our local motion. Laniakea places that older region inside a wider network of converging flows. One name describes an important concentration within the pattern. The other describes the immense basin traced by the pattern itself. The newer map didn't make the earlier clue irrelevant. It showed where that clue belonged. There's also no reason to treat the present outline as an eternal border. These flow lines are reconstructed from measurements, models, and the distribution of matter we can observe. Better data can sharpen them. Different methods can adjust where a dividing surface lies. And because cosmic expansion continues, the whole basin shouldn't be mistaken for a single permanently bound object that will someday collapse into one place. Our own galaxy sits within this flow-defined region, carried along with a local group inside a pattern far too large to see directly. We know it through accumulated redshifts, distance measurements, and the small departures from cosmic expansion that reveal gravity at work. So if Laniakea has no glowing rim and no fixed wall, where inside this immense basin are we? You might place us somewhere near the bottom. That seems natural. If the Milky Way belongs to a cosmic basin, then surely we must be sliding toward its deepest point. But our place on the map is much less dramatic. The Milky Way lies near the rim of the Laniakea basin, not near its center. Imagine standing high in a broad watershed after a light rain. You're inside the watershed because water from the ground beneath you joins a particular drainage system. Yet you may be much closer to the ridge than to the lowest valley. A few steps across that ridge and the water would take another route. Being part of the watershed doesn't put you at the bottom. It tells you which way the nearby slopes guide the flow. Our position in Laniakea works in a similar way. The measured motions of galaxies around us fit within one reconstructed pattern of flow. That pattern places the Milky Way close to a dividing region, where neighboring cosmic flows begin to belong to a different basin. We're part of Laniakea because of how our motion connects with the surrounding motions, not because we occupy some privileged seat in the middle. So there's no need to imagine the Milky Way on a straight shoot toward one enormous center. Gravity shapes our motion, of course, but our path sits inside an uneven landscape influenced by matter at many distances. The flow lines curve, nearby groups tug on one another. Larger concentrations shape the wider pattern. Cosmic expansion remains part of the motion too. And this isn't one frozen route painted across space. The map gathers many galaxy motions into a shared pattern, then shows how those motions relate. Our location near the rim describes that relationship. It doesn't turn the rim into a track, or the center into an appointment we're bound to keep. It's closer to following a winding stream across a hillside than dropping through the drain in a sink. That takes some of the doom out of the view. Laniakea isn't a vast funnel with us trapped halfway down, and our place near its rim isn't a prediction of where the Milky Way must eventually end up. It's a relationship found in the present map. This galaxy, in this measured velocity field, lies near the edge of this particular pattern. There's something useful about how ordinary that sounds. Older maps of the large-scale universe encouraged the eye to search for a throne, a dominant center, one great destination pulling everything toward it. The flow map is better partly because it's less theatrical. It replaces the throne with terrain, and terrain allows for bends, ridges, neighboring slopes, and paths that only make sense beside other paths. Even the word edge needs a gentle touch here. It doesn't mean a sharp border passing through empty space like a wall. It means the reconstructed flow changes allegiance across a region. On one side, trajectories join the pattern we call Laniakea. On the other, they join a neighboring pattern. Where researchers draw that dividing surface depends on the measurements available and on how the velocity field is reconstructed. That leaves us in a rather fitting place. We're residents of Laniakea, but not its centerpiece. We sit near a quiet boundary in a map made from motion, looking inward and outward at once. And when newer surveys traced those motions across still greater distances, did Laniakea remain the largest basin the map could reveal? The first answer came from adding more dots, a great many more. Imagine trying to see the shape of a river by dropping a few leaves onto its surface. With 10 leaves, you might notice the general direction. With thousands, you begin to see slower channels, dividing currents, and places where the water spreads apart. The river hasn't changed. Your view of its motion has. Something similar happened after the first Laniakea map. Astronomers didn't simply reconsider the same collection of galaxies and choose a grander name. They built a deeper, denser catalogue of galaxy distances. Each measured distance gave them another point where they could compare a galaxy's observed motion with the motion expected from cosmic expansion. The result was Cosmic Flows 4. The catalogue compiled distance measurements for 55,877 galaxies, arranged into 38,065 groups. In plain language, that meant tens of thousands of measured points scattered through the nearby universe. The old sketch was becoming a mesh. Grouping is important because galaxies often travel together. A cluster can contain hundreds or thousands of galaxies, all sharing much of the same large-scale motion. Treating every member as a completely separate marker would make a crowded region seem more informative than it really is. So researchers combined related galaxies into groups, rather like noticing that 50 leaves are caught in the same little eddy. You still record the eddy carefully, you just don't pretend it represents 50 independent rivers. With that thicker net of distances, astronomers can estimate the velocity field across a much larger volume. A velocity field is simply a map showing how motion changes from place to place. There isn't one arrow pointing toward a single cosmic drain. There are arrows everywhere, inferred between the measured points, bending toward dense regions and away from emptier ones. More measurements make that reconstruction finer. Broad patterns become easier to separate from local jostling. A boundary supported by many nearby measurements is less likely to shift because one distance estimate changes. Large features can be followed farther before they fade into poorly sampled territory. But the map doesn't become a photograph. Distances to galaxies are difficult to measure, and some parts of the sky remain better sampled than others. Researchers still need mathematical models to infer what happens between the points. They must smooth over small irregularities without washing away genuine large structures. Change those choices, and some borders move. So Cosmic Flows 4 brought greater reach and better stability, but not perfect certainty. That distinction is easy to lose when the finished map appears as clean-colored regions. Nature did not supply the neat outlines. The outlines come from our best reconstruction of a flow that remains continuous. And the denser the map became, the less the local universe resembled a set of objects falling toward one final destination. It looked more like a landscape of motion. Flows gathered into several basins, other regions pushed trajectories apart. Between them lay dividing surfaces where neighboring streams quietly chose different routes. Laniakea was still there, recognizable within that landscape, but it no longer had to be the last or largest shape worth naming. Once the measurements reached beyond its familiar currents, the map could contain several watersheds at once, nested inside patterns drawn across a much greater depth. So when astronomers followed this richer field beyond Laniakea, what larger pattern did our basin appear to belong to? Once you stop looking for one destination, the map begins to show something more balanced and more surprising. Imagine a terrain map after heavy rain. Water doesn't all head toward the lowest point on the entire continent. It follows the local slope, gathers into separate drainage basins, and crosses invisible boundaries that decide which stream belongs where. A stream can be part of one watershed even when another valley begins just beyond the ridge. The reconstructed motions of galaxies can be read in much the same way. Astronomers now identify 6 large watershed superclusters in this dynamic map. Each one is defined by a family of galaxy flows gathering within its own broad basin. The boundaries aren't walls, and the galaxies don't know they've crossed from one named region into another. The names simply help us describe where neighboring paths separate and begin following different slopes. That changes the old view. Our motion isn't one arrow aimed at one enormous object. It's a route through a landscape, shaped by several concentrations of matter at different distances and on different scales. Some slopes have a strong effect nearby. Others become clear only when the reconstruction reaches farther out. There may be a neat arrow at any one point, but the map producing that arrow is anything but simple. And a terrain map has high ground as well as valleys. In the cosmic version, that high ground can correspond to a region containing less matter than its surroundings. Cosmographers sometimes call the resulting feature a repeller. The word sounds as if something hidden there is pushing galaxies away. Nothing needs to be pushing in that cartoon sense. There is no anti-gravity object sitting inside the void, politely directing traffic. Gravity still attracts. A region with relatively little matter simply provides less attraction from that direction. Meanwhile, denser regions around it pull more strongly. Put those differences together, and galaxy paths tend to spread away from the emptier side of the landscape. Emptiness can shape motion without becoming a new kind of force. It changes the balance of the pulls already present. That description has become specific enough for researchers to identify central repellers associated with the Bhutas and Sculptor voids. These are not new destinations competing with familiar attractors. They're useful parts of the same reconstructed velocity field. One side of a flow may be guided by where matter is concentrated, while another is shaped by where matter is scarce. This is a more adult map than the old attractor story. The older version offered a satisfying dot. Find the hidden mass, draw an arrow, and call that the answer. The newer version asks us to keep track of the whole terrain. Valleys gather motion, higher regions divide it. Watersheds tell us which flows belong together, and the pattern you see depends partly on how much of the landscape your measurements can reach. So where are we going? At any given moment, the Milky Way has a measurable velocity. But explaining that velocity means adding the slopes around us from nearby structures to much larger ones, rather than naming one final place. The answer is one gravitational field spread across the local universe, with crowded regions and empty ones, both helping set the route. If our motion belongs to one continuous landscape rather than one cosmic target, how far must that landscape extend before the remaining pull is fully accounted for? Complexity only earns its keep when it gives you a simpler answer at the end. Otherwise, you've traded one confusing map for a larger confusing map, which is an impressive way to spend several decades and still leave everyone pointing in different directions. The newer maps do something more useful. They turn a collection of apparent destinations into a single pattern of motion. Galaxies don't simply aim at one marked spot. They move in streams. Those streams gather into basin-like regions, bend around overdense areas where matter is crowded, and move away from underdense areas where matter is sparse. The terminology can sound like a box of spare parts. On the map, though, everything fits together. Think of a relief map showing hills, valleys, and slopes. You may keep improving the measurements and redrawing the contours, but you no longer need a rumor about one hidden mastermind controlling every river. The terrain explains why the water follows one route rather than another. A relief map is easier to trust than that rumor because each piece can be checked. Measure another distance, add another galaxy's motion, see whether the inferred slope still sends the flow the same way. The view grows through repeated measurements, not through loyalty to one dramatic name. This is what higher fidelity cosmography has changed. It hasn't merely supplied more possible answers, it has changed the kind of answer that makes sense. In 2023, cosmographic work described by Dupuy and colleagues treated our region through these connected flows. The useful result wasn't another grand label to place beside the others. It was the growing ability to read many measured motions as parts of one field. One field, not one target. That idea is simple, but it isn't vague. A field has structure. It has directions, boundaries, gathering places, and dividing lines. It lets astronomers compare the measured motion of galaxies with the distribution of matter around them. It also includes both sides of the terrain, crowded regions drawing matter toward them, and emptier regions helping decide which routes the surrounding flows can take. So the modern answer isn't that we've lost the destination in a fog of complexity. The destination was too blunt an idea for the motion we were trying to explain. Our galaxy belongs to a structured flow, and that flow belongs to a larger pattern. The names on the map remain useful landmarks within it. None has to become the final object toward which everything is simply falling. Imagine the whole local map settling into readable terrain. The scattered labels stop competing for the role of chief suspect. Each becomes a feature with a measured place in the landscape. That is a quieter view and a more useful one. It lets the motion remain complicated without making the explanation evasive. The map is still being refined. New distance measurements can shift a boundary, sharpen a stream, or change how far a particular influence appears to reach. Cosmography isn't a finished portrait nailed to the wall. It is a measured reconstruction, and better measurements can still alter the terrain. But refinement doesn't erase the plain conclusion already in view. The Milky Way's motion can be described without turning one region into a cosmic drain. We are moving through a gravitational landscape whose structure extends across many scales. The explanation doesn't have to end at one point. So, with the extra names set aside and the map finally allowed to act like a map, what is the Great Attractor actually attracting? The Great Attractor is still attracting us. The old name hasn't become a lie just because the modern map is larger. That is important because you were promised an answer about a famous place in the sky. It would be a little unfair to reach the end, unfold a more complicated map, and quietly pretend that place was irrelevant. It isn't. The Great Attractor names a real region in our part of the universe, and the mass gathered there helps shape the Milky Way's motion. What has changed is the size of the claim. When astronomers used the name in the late 1980s, they were working with the flows they could measure and the structures they could identify. Dressler and his colleagues saw galaxies moving together in a way that demanded a large gravitational influence. Lyndon Bell and his colleagues gave that influence its memorable name. Neither team was naming a single hidden object with a neat edge. They were identifying a region in the gravitational landscape from the motion around it. Modern cosmography keeps that region on the map. It hasn't been rubbed out or relabeled as an embarrassment. You can still point toward it. You can still describe nearby galaxies, including ours, as responding to mass in that direction. The old marked patch still glows. It just sits inside a much broader pattern now. Think of an older map that marks a mountain range but ends at the border. Later surveyors extend the map and discover more ridges beyond it, along with valleys that guide every river in the area. The original mountain range doesn't vanish. Its slopes are real. Its effect on the water is real. It simply wasn't the entire watershed. A larger map changes the explanation without making the first landmark imaginary. The Great Attractor is like that. It remains part of the truth, not the whole of it. So the famous name survives, but with gentler boundaries. It describes one important concentration within a larger field of clusters, filaments, walls, and emptier regions. Their combined pull helps carry galaxies along broad streams. The Great Attractor contributes to our motion without serving as the lone destination of everything nearby. That corrected version is less theatrical, though it's also more useful. We haven't found a cosmic plug hole behind the Milky Way. We found a landscape, and one of its most important regional features still bears the old name. The title points to something real. It only becomes misleading when the region is inflated into one object doing all the work. There is also no perfectly clean way to assign each feature its share. Gravity overlaps. The boundaries between regions depend partly on how distances and motions are measured, and those measurements continue to improve. A galaxy's path doesn't arrive with labels showing which cluster supplied each fraction of its speed. Nature has declined to itemize the bill, which is inconvenient for astronomers and rather typical of nature. We can say with confidence that the Great Attractor belongs in the explanation. We can also say it doesn't own the explanation. The remaining uncertainty lies in the proportions, the borders, and the exact reach of each surrounding structure. That isn't a retreat from the answer, it is the shape the measurements support. And once several regions are pulling at once, how do astronomers decide how much of our motion belongs to any one of them? After a long explanation, it's natural to want a neat final number. 20% from here, 30% from there. Put the shares in a neat chart, make them add up to 100, and close the case. The trouble is that gravity doesn't leave separate fingerprints. We see the motion of galaxies, estimate their distances, map the matter around them, and then reconstruct the flow that could have produced what we observe. It's a little like looking across a sharp mountain landscape, while some of the contour lines are still being refined. The mountains are real, their positions are clear, but the exact slope of every patch of ground can still shift as better measurements arrive. Modern reconstructions give us a strong overall view. Our motion belongs to a broad pattern spread across the local cosmic network. Nearby structures contribute. More distant concentrations contribute too. The region traditionally called the Great Attractor remains part of that pattern. None of these needs to disappear merely because its exact share can't yet be printed beside its name. The uncertainty sits around the division of influence, not around the existence of the larger gravitational landscape. Some uncertainty comes from sampling. We can't measure every galaxy equally well, and distance measurements carry errors. A small error in distance can change the motion we infer for a galaxy. When thousands of those measurements are combined, the main currents remain visible, while finer boundaries become less certain. Then there's the hidden sky. Dust, gas, and crowded stars in the Milky Way obscure part of our view. Astronomers can work around that obstruction using radio surveys, infrared observations, and mathematical reconstruction. But working around a curtain isn't quite the same as removing it. The broad structures behind the Milky Way can be recovered, though their details may remain softer than those in cleaner parts of the sky. Model choices matter too, especially near the margins. Researchers have to decide how to turn an incomplete set of galaxy distances and motions into a continuous flow field. Reasonable methods can agree on the large pattern while assigning slightly different borders or strengths to individual regions. As the data improve, those differences narrow. They don't usually erase the landscape and replace it with another one. Instead, the broad map holds while its finer contour lines are adjusted. That distinction is important. Uncertainty about the exact partition isn't uncertainty about whether the distributed view exists. The map is secure enough to reject the old idea of one concealed object doing all the work. What remains open is the finer bookkeeping. How much pull belongs to each structure, where one region's influence blends into another, and how far the reconstruction should extend before the answer settles. There's something reassuringly adult about leaving those shares fuzzy. A set of polished percentages might feel briefly satisfying, but invented precision would make the answer weaker, not stronger. Science earns trust by showing where the contour lines are firm and where the pencil is still moving. So the final view can be both clear and unfinished. We live inside a connected gravitational landscape, and our motion reflects several parts of it at once. The major terrain is visible. The exact shares are still being honed. If nature never divided the pull into neat pieces, why should the most accurate answer pretend that it did? After all those names and maps, the answer becomes surprisingly plain. We aren't being dragged toward a single hidden object. We're moving through a gravitational landscape, shaped by matter spread across different distances and scales. Nearby concentrations contribute. The obscured Great Attractor region around the Norma cluster contributes. The much larger concentration around Shapley contributes too, and all of them belong to the wider local cosmic network that surrounds us. Think of it less like water circling a drain, and more like rain crossing a broad hillside. The water responds to the whole shape of the ground beneath it. A nearby hollow can bend its path. A distant slope can set the larger direction. Ridges and valleys merge into one continuous surface. Asking which single patch of ground moved one particular drop misses how the hillside works. Our motion is like that. One measurable flow, shaped by structure across a large connected region. The map improves as astronomers measure more galaxies, estimate their distances more carefully, and see through parts of the sky that dust once hid. With each better map, the old one-object answer gives way to a broader view. That isn't science retreating from certainty, it's science becoming more faithful to the landscape. The Great Attractor still has a place in that view. The name points toward a real concentration of matter in a difficult part of the sky, near the Norma region. It helped astronomers recognize that nearby galaxies were sharing a large-scale motion that simple expansion couldn't explain by itself. But the name also made the answer sound tidier than nature had arranged it. There was never one enormous mouth waiting in the dark, swallowing everything around it. There was structure, partly hidden, embedded in still more structure. Shapley widens the frame. It lies farther away and contains an immense concentration of galaxies, adding to the flow measured across our part of the universe. Yet Shapley isn't the final stop either. It sits within the same network of clusters, filaments, walls, and emptier regions that gives cosmic matter its uneven shape. Our path crosses that whole terrain. It doesn't come with a neat destination label. That may feel less satisfying than circling one object on a map. It is also a better answer. The universe has no obligation to organize its gravity around the kind of explanation that fits comfortably in a headline. Sometimes the grown-up version is a landscape instead of a landmark. You lose the dramatic bullseye, but gain a map that more closely matches what the galaxies are doing. And that shift changes the answer. A landmark invites us to imagine arrival, as though our galaxy were traveling toward one final place. A landscape gives a calmer view. Our motion belongs to the structure around us, just as the motions of other galaxies belong to their surroundings. There is no need for a hidden monster or a cosmic finish line. There is simply matter, unevenly spread, shaping motion across enormous distances. And the map will keep improving. New measurements may sharpen the influence of one region or redraw the edge of another. They won't need to turn this back into a tale about one concealed monster. The quieter view already holds. We move within a distributed gravitational flow, shaped together by nearby overdensities, the hidden Great Attractor Norma region, larger structures including Shapley, and the wider local cosmic network. That is where the answer can rest. Not on one object, but within a landscape we are learning to see more clearly. We began with a very natural view. If whole galaxies are moving in roughly the same direction, then something enormous must be pulling them. Give that something a location, hide it behind the crowded light of the Milky Way, and it starts to feel almost like a single object waiting to be found. The Great Attractor was a useful name for that view. It still names a real region where a great deal of matter is gathered. Its gravity contributes, but the name makes the answer sound tidier than the universe has turned out to be. You aren't being carried toward one hidden beast in the dark. Neither is the Milky Way. We're moving through a gravitational landscape shaped by matter spread across an enormous volume of space. Some regions contain more galaxies and more mass. Others contain less. Nearby concentrations pull, emptier regions change the balance, and more distant structures add their influence. Our motion is the combined result. Think of rainwater crossing uneven ground. You might watch one narrow stream and assume that a single hole is drawing it in. Then the wider survey arrives, and you see slopes, ridges, shallow basins, and several channels feeding one another. The stream was real, its direction was measurable, but the landscape was doing the guiding. That is much closer to the situation around us. The Great Attractor region belongs on the map, but it isn't the entire map. It's one important part of a much larger pattern of matter and motion. Once that pattern is included, the old mystery doesn't vanish. It becomes better shaped. There's something quietly reassuring about that. Our galaxy isn't breaking loose from the universe, and it isn't plunging towards some unknown object that has escaped every telescope. It's responding to gravity on a scale too large and too uneven for one simple name. The motion is extraordinary only because the landscape is so immense. And the map is still improving. Astronomers keep building better catalogues of how galaxies move compared with the general expansion of space. They keep finding ways to recover information from the parts of the sky hidden by our own galaxy. Each new measurement can sharpen a boundary, adjust the weight of a region, or reveal another piece of the surrounding terrain. That uncertainty doesn't undo the answer. It tells us where the edges remain soft. We know enough to say that no single concealed mass explains everything. We also know that the Great Attractor wasn't an imaginary mistake. It was an early view of one slope, seen before enough of the country around it had been surveyed. Astronomy often leaves us with answers that are harder to draw in our heads because they're more accurate. One object is easy. A layered gravitational landscape is less convenient, but nature doesn't owe us a villain with a clear outline. So tonight, as Earth turns, the Sun moves with the Milky Way, and our galaxy travels with its neighbours, we're following a map written in gravity. Much of that map can be measured. Some of it remains hidden behind the bright, dusty band above us, and some of its lines will shift as the surveys improve. But the main shape is already steady enough to trust. There is no lone monster waiting behind the Milky Way. There is matter, spread unevenly across the dark, gently guiding the motion of galaxies through a landscape we are still learning to see. The map isn't finished. Our place within it is becoming clearer,